Welcome to this explainer. Today, we're going to bridge a massive, totally invisible gap. We're talking about the space between human language and raw computer processing. We are going to explore the foundational digital alphabet, that hidden translation layer that literally makes all modern computing possible. Let's get right into it. So let's dive into a real engineering marvel. It's something every university student typing a frantic late-night essay relies on every single day without even knowing it. Think about it. You press a plastic key with an ink letter stamped on it, and boom, instantaneously that exact letter appears on a glowing screen. But underneath that keyboard, there is no alphabet, there is no ink, there is just metal, silicon, and electricity. So how exactly does a machine made of wires understand the letter A? Well, herein lies our core problem. Humans and computers do not speak the same language, like not even close. We humans communicate with highly nuanced, expressive letters, words, and these complex grammatical structures. But machines, they are fundamentally simple. At their core, they only understand machine language, and that is just binary, ones and zeros, pure on and off switches. If we want these machines to process our human thoughts, we absolutely need a universal translator. Here is our roadmap for today. First up, the human-machine language barrier. Second, meet the digital alphabet. Third, decoding the ASCII table. Fourth, translating to binary code. And finally, ASCII's lasting digital legacy. All right, section 1, the human-machine language barrier. So without a translation bridge in place, your keyboard and your computer's processor are basically speaking two completely incompatible languages. When you type that letter A, your keyboard doesn't, send a tiny picture of an A down the wire. It sends a burst of electrical pulses. And without a strictly agreed upon rulebook for what those pulses actually mean, the processor would just see random noise. It's the great divide of computer science, figuring out how to turn a physical action into actual digital meaning. Moving on to section 2, meet the digital alphabet. Now, ASCII acts exactly like the ABCs we learned as kids. But it was designed entirely for early computers. It stands for the American Standard Code for Information Interchange. Simply put, it's a standardized numerical alphabet. It is the agreed-upon dictionary that tells the computer, hey, when you receive this specific numeric signal, it means this specific human letter. It's a total game changer. 128. This single number represents the exact amount of characters available in the original standard ASCII set. You see, early computer scientists had to be incredibly efficient with memory, so they settled on exactly 128 slots to represent all the essential keystrokes needed for digital communication at the time. Sure, later on, as memory got cheaper, this was expanded to 256 characters. But those original 128 slots, they laid the permanent groundwork for literally everything we do today. And notice, this isn't just the alphabet. Meticulously packed into those 128 slots are control characters. Invisible commands like enter to start a new line, or backspace to delete. It includes all your standard punctuation marks, your commas, your exclamation points, and, very importantly, it separates the uppercase alphabet from the lowercase alphabet, treating them as entirely different entities. The whole shebang is right there. Let's hit section 3, decoding the ASCII table. Okay, let's dive into the actual numbers here, where you can clearly see the translation in action. Think about how capital A is explicitly mapped to the decimal number 65. Then capital B is 66, C is 67, and so on. But notice the massive jump for the lowercase letters. The lowercase counterpart, A, shifts all the way up to the number 97. To the computer, a capital A and a lowercase a aren't just the same letter with different formatting. No way. To the machine, they are two entirely distinct numbers. And you know what? This numerical assignment solves another massive problem, alphabetizing. Have you ever wondered how a computer instantly sorts a massive spreadsheet of names from A to Z? Well, it doesn't actually know the alphabet. It just looks at the underlying ASCII numbers and sorts them from lowest to highest. Assigning sequential numbers makes alphabetizing a simple greater than or less than math problem for the machine. It is honestly incredibly elegant. Which brings us to section 4. Translating to binary code. Let's watch this micronarrative unfold step by step. Step 1, you press a key, let's say the capital A. Step 2, the ASCII standard acts as the translator, recognizing that keystroke and assigning it the decimal number 65. Step 3, the computer takes over, instantly breaking that human-friendly decimal numbers down into manageable binary code. So, 65 becomes a very specific sequence of ones and zeros. And that sequence is 01000001. Now, this isn't just a random string of numbers. It is the precise arrangement of 8 on and off electrical switches required to store a single capital A in your computer's memory. A 1 means an electrical charge is present. A 0 means it's not. To put that into perspective, every text message you've ever sent, every single essay you've ever written, is just millions upon millions of these exact 8-bit patterns firing in sequence at lightning speed. Pretty mind-blowing, right? Finally, Section 5, ASCII's lasting digital legacy. So while ASCII was the absolute bedrock foundation of digital communication back in the 1960s, our human need to communicate inevitably outgrew it. I mean, ASCII was very American-centric, hence the A in the acronym. By the 1980s, we realized we needed more symbols, which led to extended ASCII expanding to 256 characters. But even that wasn't enough for a truly globalized digital world. By the 1990s, the computing world established Unicode, which is this incredibly expansive system designed to handle the language needs of the entire planet indefinitely. Which leaves us with a fascinating thought. If ASCII gave us the first 128 characters to build the digital age, how does its massive successor, Unicode, manage to translate the entire world's complex communication, from intricate Arabic scripts to the exact emoji you send your best friend, into those same simple ones and zeros? It's a phenomenal question and exactly where this foundation will take you next. Thank you so much for joining me for this explainer.